Good morning, I'm Charles Reese. Today I'm going to be talking about how we use Kafka and Clojure at Funding Circle. So Funding Circle is a small business loans platform. We allow investors to lend directly to small businesses looking for finance. We're a platform. And we operate in 4 markets and have originated over £5.6 billion in loans since founding. And we're still growing. So I'd like to talk a little bit about Kafka and how we use it. But before I do that, I want to talk about how it's typically used. So Kafka 101, if you will. So Kafka is a distributed publish-subscribe messaging system. Let me break that down. Suppose I have some data I want to share, and I don't have all of it right now. I might want to add more later. So I can create a topic, and I can publish what I have. So let's say you want to share, I don't know, recipes. And so I can create a topic called recipes. Thank you. Or you might want to share stock tips. That's always fun. I've got a topic for that. You might want to share advice. Then anyone who cares about what your data is can subscribe to whatever they want. No one seems to want advice. So if I'm sharing, I'm a publisher, and if I'm just taking, I'm a subscriber. But I could be both. And in the Kafka docs, you'll typically hear these referred to as producers and consumers. But it's basically the same thing. So for the recipes and stock tips topics, Kafka maintains a partitioned log that looks like the diagram on the right. The boxes correspond to individual records. And each of the topics has 2 partitions where order across records is guaranteed. So first partition, second partition. Within a partition, as I said, there's an ordering guarantee, and each record has an offset number that's its index in the log. Now, topics can have any number of partitions. My example just shows each topic having 2, but it could be whatever you want. So I'm a publisher. I'm a producer. When I publish a record, Kafka appends it to the log on whatever topic and partition I want. That's something I get to decide as the producer. If I'm a subscriber, a consumer, I just need to keep track of the records I've seen. And the latest offsets the position in the log for the topics that I care about. They're like bookmarks. So I've talked about what Kafka is and how it's typically used. And for the rest of this talk, I want to talk about how we use Kafka at Funding Circle. I want to talk about Kafka as a platform for stream processing. So what happens if you're both a producer and a consumer? What if everyone is? Right? You have node, for example. Node 1 is consuming from a topic and producing to a topic. Node 2 is producing from 2 topics. Maybe it's doing a join, and it's consuming from 2 topics, producing to 1. And we have a third node. And together, these nodes form what we call a processor topology. And we can even give them state. Now, this used to be hard, or hardish, but recently it's become much easier because now we have the Streams API. And this is actually part of Kafka itself as a library. So this API is relatively new. It's only been around since about 2016. I want to take a look at a couple of the interfaces. So an important one is a K-stream, and it's a record stream of key value pairs that corresponds to an event. So this happened. I have a new recipe, or what have you. Another important interface is the K-table interface, and that's a changelog stream. So you can think of these like database tables, more like your traditional Postgres or MySQL database table. Every record will have a key and value, and if a new record arrives with the same key, it will replace the previous one. It won't actually do that until compaction occurs, though. So if you set it, but the semantics of the K-table are set up so that compaction will be enabled, and so when it occurs, that record will replace the previous one. And I guess the last important point I want to touch on is the topology builder. It's really just used to construct topologies. So it's a data structure in which you perform operations on it, and it will attach different nodes. And at the end, you can pass that to an instance of the Kafka Streams instance and use that to start the app. So I was going to go and take a look at the K-Streams interface. I just don't want to run into other issues with the AV. Is that showing a web browser for you? Yeah. Cool. This is the Kafka Streams interface. I'm not able to scroll down, but for the K-Stream instance. So you can see there are a lot of member functions there, things like flat map values, flat map, reduce. You can do all sorts of things, and if you're used to using Clojure, this should be very familiar. You able to see that? No, it's switched off. Okay. How about that? Okay, so this is an example of the word count demo in Kafka. So it's written in Java. It's all right. It's Java. I'm not going to dwell too much on it. You can already write Kafka Streams applications in Java. But I think the next thing I want to talk about is, let's see, how can I get back to the, let's just mirror displays now. And all right. So I want to talk about a little bit why we use Clojure. It's got immutable data structures. Kafka topics are kind of like immutable data structures. Composability. I think the key factors for us, though, are the Java interop, which is really important if you're developing on Kafka, because Kafka is a rapidly evolving platform, and you need to be a first-class citizen in that ecosystem. The other factor is dynamic development, and I'll talk a little bit more in detail about that later, but I think that's a huge win for us, is that we were rapidly able to prototype, deploy a topology, restart it, and so on. So this is what we built at Funding Circle. We have rebuilt our marketplace in terms of Clojure and Kafka. We have systems that process orders, take payments, service loans, keep track of where the money is. That one's very important. And then all of those are connected to Kafka, and our edge services, we have the data lake, takes in all of the events that are happening, metrics gathering. We have a front end that we can use to both send commands and also materialize views, and APIs for the same. And the systems above the line are all stream processing applications written in Clojure, running Kafka Streams applications, and they use RocksDB for internal state. So this is a big win for us because it allows us to manage all of our side effects against one system, Kafka. Okay. So we've been doing this for a while, and I'm happy to announce today that we want to get back to the community. We are ready to release our Kafka Streams wrapper for Kafka Streams. It's called Jackdaw. And I'd like to take you through that now. Can you see that all right? All right. So this is Jackdaw. It's got a couple of interesting namespaces. Let me just take you through the source here. So can you see that all right? Yeah. All right. Bigger? All these AV issues. Let me see if I can. Command plus. How's that? Okay. So a couple of the namespaces that are interesting. We have the admin API, which allows you to create and manage topics. We have the client API that allows you to produce and consume records. These are pretty thin wrappers around the existing Java APIs that are provided by Confluent. We also have a Streams API that wraps all of Kafka Streams, or at least the bits that we're using, but it's getting better every day. And we have a a library that we use for creating surdays. So our surdays library allows you to serialize and deserialize to the wire for Eden, JSON, and Avril. And it works with the Confluent Schema Registry to manage schemas. And then we have a test namespace that's actually in development by a fellow in London called Andy Chambers that allows you to do integration testing. So you put a record onto a running Kafka instance. It could be locally, it could be in a staging environment. You produce records, you pass it through a series of topologies, and then you consume the results. So it's pretty cool. More on that one soon. That one's not in the initial release, but it will be probably next week, maybe. So that's Jackdaw. And here are the core namespaces. I just talked about those. So I'd like to do a little demonstration just to show you how we use Kafka Streams from Clojure. See if I can get rid of this. Can't. Can you all see that? Okay, I'm working on it. How's that? Bigger? Okay. No. All right. So this is a sort of a reformulation of the Java word count example written in Clojure using Jackdaw. A couple of interesting. I'll just walk you through the code really quick. It's not very long. So we have a function that returns a topic config. This is kind of the core data structure of Jackdaw. It allows you to, in one map, represent anything having to do with the topic. So things like what it's called, how many partitions it has, its replication factor, which has to do with how it's replicated across the cluster, and then the key and value surdays that you will use to serialize and deserialize records. So for all of these examples, I'll be using the Jackdaw Eden serializer. So you just give it a Clojure map. It serializes it to bytes, turns it back into Eden when it consumes a record. And then we have an application template. So the app template just contains the config. It's got a name. How do I connect to Kafka? That's the Bootstrap servers primitive. The build topology function is actually where the topology will be declared and constructed using the DSL. But the builder is actually, this is just a stub, so we'll add to it later. And then we have functions to start and stop the topology. So I believe I'm already running Kafka, but I might not be, so let's start it up. So this is just a wrapper around Confluent's CLI. You can use it to start different services, and I have it wired up to set up Zookeeper and Kafka. Zookeeper is what Kafka uses for a dependency. So that's started, and now I can start the topology. All right, so what this does is it creates any topics the topology used. They were declared above as input and output, and then it starts the topology using whatever builder we've specified. So we can see what topics were created, input and output, something for metrics. All right, so let's get started. So the first thing I want to do is I want to walk you through an example we call pipe. It's what it says. It takes data from the input stream, logs it, and then maps it to the output stream exactly as it was. Let me find my REPL. Okay, so if I evaluate this, and then I reset, and this here is really the heart of the workflow. So what we've done now is we've deleted whatever topics we had, we've stopped the topology, we've removed any internal state, and then we spin everything back up. Kafka remains running, but the application itself has been stopped and restarted. Take that, Java. Okay. So now what I'm going to do is I'm going to publish a record, and it contains a key of nil, because you need a key, but we don't have to actually specify anything about it. And then this is a pipe for the value. There's no output there because publish doesn't return anything, but we can now consume from the output stream. We can see we have copied our data over from the input stream to the output stream. And in the window on the lower right, you can see that it logged what it saw on the input. This is a pipe. We can reset. and we can see that the output is now empty. We've recreated the topics with no data in them. So that's also useful if you just want to try something. Okay, I've cleaned up, let's try something else. Okay, So now I want to talk about a little bit, this is actually kind of an important part of our workflow, which is we don't really start with Kafka Streams and Jackdaw. We actually start with pure Clojure functions. So we can do a lot of our prototyping for this word count feature by just writing pure Clojure code. So I'm going to evaluate this. So this is a function that just takes an input stream and splits it along the white space. Okay? And then this is a function that's going to simulate what our topology will do in the way that's approximates in the way that it does it. So it's going to group by the words. After it splits the lines, it's going to group by the words. And then it's going to reduce, counting the occurrences, collecting them out. And so what I'm going to do here is I'm going to show you what the output looks like if I have two strings, concatenate them together so that we can get all the words in one record, and we can run counts on it. So we can see that in the return, we get a map. The keys are the words, and the values are the counts. So streams occurs twice, Kafka occurs twice. So now we're going to do a real demo through Kafka. So this is our build topology function. And it's doing a few things. First, it's doing the same thing that pipe did. It's creating a k-stream, from the input topic. And then it's piping that through a method called flatMapValues. And for each value or each record in that stream, it's going to call split lines. And then produce a number of records equal to how many records you end up with at the end. So now we'll take one record and turn it into many, one for each word. Then it's going to group by the value, the word, and it's going to count. And then it's going to convert that back to a k-stream because counts is a k-table, and put it on the output stream. So I've evaluated, reset, and I'm going to publish a couple of records. So all streams lead to Kafka. It was too fast. There. So now it's passed through our topology. Everything occurs once, but now when we add some more data, we see that Kafka and streams now have count of 2. So cool. Now one thing I want to point out about this is that streams occurs twice in the output stream, and that's because we're seeing the entire history of the record stream. And the first time the topology saw streams, it gave it a count of 1. And the second time it sees it, it gives it a count of 2. This is a record stream, so there's no compaction in the topic. So you're going to see the entire history of all of the changes that occur. So if you want to actually see something that looks like our Clojure code, you need to convert it to a map and sort. So then it'll do the compaction in the code. One thing I want to show is the topics that exist in this topology. So you can see there are some additional topics besides what we had in pipe. And the one that's interesting is word count, k-stream, aggregate, state store 3, changelog. So this is where the state is stored. This is the k-table. And we can actually consume directly from that topic. And we can see it has the same values as the output stream. If compaction was enabled on this topic and compaction had occurred, you would lose the instance of streams 1, Kafka 1. We would only have the latest state. All right. So let's do not a big data problem, but a bigger data problem. I have a copy of the metamorphosis, and I'm going to I'm going to split it into a series of records along the new lines, and I'm going to produce these to the topology. So I've already reset to clean up my data. There we go. Let's see if we get to the end. We're not done. Getting there? Get in there? There, we're done. Give it a second. Now when we consume from the output stream, we see the word counts for the metamorphosis. So there you have it, Kafka and Kafka. Okay. I'd like to take you through another example that's a little bit closer to what we do at Funding Circle. So I call this one the simple ledger. So this is essentially a topology that will take a series of ledger entries that we want to record. It's a double entry bookkeeping system, so each entry will have a debit, a credit, and an amount, where the debit and the credit say what accounts you want to take the money from, what account you want to give the money to. All right. and it will output a series of debits and credits that were actually recorded. So the left side of the entry, the right side of the entry, and each request event can contain multiple entries. So again, we have a topic config, that's the same. The app config is more or less the same. I've preceded the build topology with pipe. Okay, so let's go right to the example. Kafka is already running, so I don't need to do anything there, but I do need to start my topology because this one is not running. There we go. So now the ledger's running as a pipe. Is it working? Let's try resetting. Okay. I'm going to restart Kafka and see if that does it. Okay. I don't know. Okay, I'm not sure what's going on with pipe, but the next example works, so I'll walk you through that one. What I want to do is I want to add input validation. One of the things that we've learned early on at Funding Circle is it's really important to understand the shape of your data on your topics, because you don't know who your consumers are, and we need to have strong controls over what data is being what your app is doing. It also helps when we're doing our prototyping. We can determine that. So this here, the data type for the ledger entries requested value contains two keys, an ID and entries. ID is just a UUID. Entries is a list of entries where each entry is a debit account, a credit account, and an amount, and these can't be the same. So I've already evaluated that. And the topology is really going to take the input topic, ledger entries requested, return a K-stream, and then it's going to call a method called branch on the input. So what branch is going to do, it's going to say, are you valid input? Where valid means, does it pass the spec? And if it's valid, it's going to put it on the valid in-memory stream, or if it's anything else, it's going to put it on the invalid memory stream. And the invalid messages go to peak, where we can log the bad input, and everything else goes on to the transaction added topic. So let's that, so reset again. And you can see if we publish a valid input, we see the data on the output stream. It's still functioning more or less like pipe. But if we send it bad input, let me find my REPL. There we go. If we send it bad input where the debit account and credit account are the same, then we can see there's no output. Oh, there is output. It's the same output we saw before. This is the valid input. But nothing new has been added. And in the log message, you can see explain data is telling you what was wrong. Foo, debit account foo, credit account doesn't work. Okay. So we've got our input validation. For the next demo, I want to take you through, I want to actually generate debits and credits. So our build topology function is going to do everything we said before, except now instead of just simply copying the data from the input to the output, we're going to pass it through a flat map that calls a function entries to transactions on the valid input stream, and that's defined basically here. So we're going to reduce over the entries, and we're going to, for each entry side, we're going to split it into a left side and a right side. So reset. Did I eval those? Let's make sure I do that. Evaluate the build topology function and reset again, just for sure. Okay, cool. So let's publish our record. Too fast. There. So now we can see a list of debits and credits. Foo gets debited by 10 cents. Bar gets credited by the same amount. Double entry bookkeeping system. Money cannot neither be created nor destroyed, right? Foo and Cucks each get debited and credited 20 cents respectively. Okay. So I can write that again, send another request. And if I do that, I see an additional 4 records to the same output stream. And there's something interesting about this, which is how can you tell that the second 4 are unique? They were supposed to be there. We have no identifying information. The way we handle that at Funding Circle is we just add IDs. So we'll add an ID that's unique for every record, and then we'll add an ID that tells you where it came from, a causation ID. So in order to do that, we don't need to change the topology at all. We can just modify the entries to transactions function. And so what I'm going to do is I'm going to map over all of the records that we're about to produce, and I'm going to attach a type 5 UUID that's derived from the input, the ID of the input record, and I'm going to attach the input record itself. And we use type 5 UIDs so that they're deterministic. That way, if we actually have a duplicate, we can use that ID to dedupe, because type 5 UIDs are deterministic. So let's reset, produce. And now you can see we've added ID, a causation ID. And the causation ID is the same for all of these records. The IDs are all unique. And if we add additional 4 records, and it's getting a little hard to see. Let's just filter on foo. And again, this is part of the power of doing everything in Clojure, because now we have the entire core library at our disposal, right? We can just filter. So we can see that what's happening with foo is it moves from -10 to -20, -10, -20. And all of the IDs are unique, but the causation ID for the last 2 is different than the first 2. So we know they're not duplicates. Okay, last one. Let's track the balances. So what I'm going to do here, and I'll walk you through this topology really quickly, this is analogous to our word count example. So what we're going to do is we're going to create a K-table from our ledger entries requested topic. We're going to check to see if it's valid, same as before. We're going to create the transactions, same as before. And now we're going to pass it through a map values to set some initial state to handle the base case. And then we're going to group by the key, the account name, in this case foo, bar, or cucks, and reduce over the account balances reducer to update the starting and current balances for each record based on what we saw before. So the starting balances will be set by whatever it was, whatever the record was for that account for the last balance, and then the current balance will just be the starting balance plus the amount of that current transaction. So let's evaluate these. And reset. And now we can see that we have 2 new fields, starting balance, current balance, and foo goes from -10, bar, and to -30 after 2 transactions. We can also show that it works across multiple records. I'm just going to filter on foo again. So we can see that foo progresses from -10 to -30 to -40 to -60. And this actually isn't terribly different from what we're running in production. It's pretty close to the same thing. I mean, there are a few bells and whistles, but more or less the same thing. Okay. I want to talk about a few gotchas. How are we for time? Partitioning strategies. How should you partition your topics? We want to make sure that order is preserved across the things that we care about. So think about our recipes example again. Say you have, say instead of recipes, the records are steps in a recipe. It would be very important that there is order preserved if we publish successive steps to the same topic. So you'd want to make sure that when you're producing that you choose your partition key in such a way that if I am publishing a record that corresponds to a recipe I already saw, that it ends up on the same partition. Okay? So it's very important that we choose our partition keys correctly because we want to maintain order across what we want to maintain order across. What about repartitioning? Let's say that you start out and you think 15 partitions, that should be good enough, right? And then it's not because you want to run 16 instances of your job and the last worker is starved. So what do? Well, just increase the number of partitions. But I've got data in the topic. If I repartition while there's data in the topic, I'm going to lose order. So you need to make sure that there's no data in your topic. We actually haven't run into this yet, but it's something we're thinking about. Joins. This goes back to partitioning again. Let's say I have 2 record streams, 1 and 2, and I want to do a stream join across the 2. The data that I have is in partition A on this topic, and I want to join, but it's in partition B on this topic. That's not going to work because they're going to go to different processes, right? So if you want to join data across 2 streams, you need to make sure that they're partitioned in the same way so that the stream join can occur. Schema evolution, schema sharing. This is actually really hard. We're still working on this. If I'm a producer, I need to have a schema, and I'm talking about Avro now, right? If I'm a consumer, I need to know something about that schema. I may need not to know everything about it, but I need to do something. What about command topics where the consumer actually owns the schema and needs to distribute that to all of the producers so they can actually use it to serialize the data? Again, we're still working on this. Topology evolution. This is a big gotcha that got us early on with Kafka Streams specifically. Do you remember that topic that we were storing the data in for our word count? Word count, K-stream, aggregate, state store, 5, changelog, right? Well, it wasn't actually 5 in the live demo. It was a different number. And that's because Kafka Streams decides what to call this topic. It's an internal topic. So if you have a topic that's baked in your production Kafka cluster, right? The state's there. You want to keep it. You want to make a change to your topology. If I add something upstream, it's going to rename this topic to something else because it's generated based on whatever topology you deploy. So this is something that got us very early on. And the solution here is to just make sure that you use the optional arguments to name your topics so that they aren't generated and dictated by the API. You can do that for almost all of the methods, not everything. So that's still something that we need to work on. How to handle duplicates. So this is actually very important for our accounting system. We want to make sure that if we have a request to record entries, that we don't do the same thing twice. Kafka has at least once to deliver guarantees. The easiest way to take care of this is just have a look-aside state store that keeps track of requests you've seen over a period of time and then establish a suitable retention policy, that coupled with type 5 UUIDs so that if duplicates are reproduced, they'll have the same ID. That strategy seemed to work for us pretty well. Offset loss. Until recently, there was a bug in Kafka that would cause your consumers to lose their offsets if they hadn't seen a record for a while. That's actually fixed in 201, so it's less of an issue now, but it's something to be aware of. So if you have a consumer that's starved for data, say it doesn't see a record on a particular partition for a month, and you only have a 4-week retention policy on your commit offsets topic, then you're just going to lose track of where you were. Very important. Event sourcing with many Kafka topics, something to be aware of. If you are treating each topic as a data type, and those events can be used to create the state of an aggregate across different topics, that's dangerous because you don't have any ordering across partitions in different topics or even partitions in the same topic. So make sure that when you're deciding how to construct your data model that you maintain your ordering guarantees. And how do we know what topics are there? So I mean, in our case, like, how do we know what's in our production cluster or what should be there? How do we get consumers and producers to agree on the partition key or the number of partitions in a topic and so on? Because whoever gets there first is going to create it, and you'd like it to be the person who's right, or at least the person who owns the topic. So in our case, we just created a repo to just house all that, but I mean, that's another thing that's still ongoing. So if you're interested in learning more about Kafka, I highly recommend Kafka the Definitive Guide. It's very well written by the folks at Confluent. It's also recent, so it tracks the current evolution of Kafka, and it's pretty accurate still. Good thing to read. And take a look at Jackdaw. We're really excited about it. We hope you are too. Give us some feedback. Let us know what you think. Thanks, and we're hiring.